Hello, this is Mr. Keppel, and this is PHYZR number 15, Wave Basics. This is from the Waves chapter, it's page number 3. In today's lesson, we'll be discussing what waves do. We'll be talking about how to make a wave, as well as a few wave vocabulary words, including frequency and wavelength. Imagine there's a still pool of water, and a finger is dipped into the pool of water about a meter away from a cork floating in the water. Now my question is, can the hand make the cork move? Even though the hand is too far away, it can't reach the cork. Can the hand make the cork move? Yes. All the hand has to do is wiggle, create a disturbance in the water, and that disturbance will be carried to the cork. We call this wiggle in time, this disturbance. We call this a wave. So what is it that waves do? They transfer energy from one place to another. In this example, the wave transferred energy from the hand to the cork. So let's make a wave. In order to create a wave, work must be done. We remember from the formula W equals Fd. In order to do work, you must exert a force across a distance. So we could apply a force on the slinky in the vertical direction. This will cause a displacement in the slinky also in the vertical direction. This will then send a pulse down the length of the slinky, and that's the energy being transferred, that's the wave. We could also apply a force horizontally, and this will cause the slinky to be displaced forwards, creating what's called a compression. And this compression, this area of where the slinky is squished, then gets transferred down the length of the slinky, and that's the energy being transferred by the slinky, that's the wave. The top wave is referred to as a transverse wave, whereas the bottom wave is called a longitudinal wave. Let's go over some wave vocabulary words. The source is the object from which the wave's energy originated. Since waves transfer energy from one place to another, the source is simply the object where this energy came from. It's the object that's transferring energy to the medium to create this wave. So in the case of this slinky wave being shown, what is the source of this wave? Where does the energy traveling down this slinky, where did that energy come from? And the answer, of course, is came from the hand. So in this example, the hand is the wave source. The hand is the object from which the energy originated. Medium. Medium is the substance or the material that carries the wave. So if wave is transferring energy from one place to another, then the medium is the material that is transporting this energy. It's the material the energy is traveling through. So in this slinky wave, what is the medium of this wave? Well, the medium is the spring, or the slinky. The medium is the material that the wave travels through. Okay, now we're going to talk more about the actual parts of a wave. And so the first part of a wave that we look at is called the amplitude. And the amplitude is the distance from the equilibrium position, that's the dotted line across the center. The amplitude is the distance from the equilibrium position to the maximum extent of the wave. So starting from the equilibrium position, we can go up, and that would be the amplitude. We go up until the very top of the wave, also known as the crest. So that distance is the amplitude of the wave. We could also, starting from the equilibrium position, go down to the bottom of the wave, known as the trough. So either one of these distances is called the amplitude. The amplitude of a wave is the distance from the equilibrium position to the maximum extent of the wave. The amplitude of a wave is important because it indicates to us the energy of a wave. So if we think back to our formula, W equals Fd, in order to create a wave, work must be done. So the work done to create the wave is representative of the energy of that wave. Let's suppose that the force exerted is constant, so let's just get rid of that and write this as a proportionality. We see that the energy of a wave is proportional to the displacement of the medium. The displacement is simply the amplitude. This shows us that the energy of a wave is directly proportional to its amplitude. If we want to increase the energy of a wave, we must also increase the amplitude of the wave. So a wave with a greater amplitude is a high energy wave, and a wave with a smaller amplitude is a low energy wave. The amplitude of a wave indicates its energy. The greater the amplitude, the greater the energy. To check your understanding, I want you in your notes to draw a picture of a low energy wave as well as a picture of a high energy wave. Make sure that you exaggerate the difference in energy so we can very clearly see that one has a lower energy and the other has a higher energy. Don't forget to draw the equilibrium position. If you're not finished drawing your waves yet, go ahead and pause this video. Here's what your wave should look like: the low energy wave and the high energy wave. Look at the amplitude of the low energy wave, and then look at the amplitude of the high energy wave. We can see that the low energy wave has a much smaller amplitude than the high energy wave. So a low energy wave has a small amplitude, a high energy wave has a large amplitude. Frequency is the number of cycles that occur each second. So here you have two waves passing by. Let's analyze the frequency of each of these waves, and we'll do this by counting the cycles and keeping track of the length of time that has passed. So you know that whichever one is cycling more slowly will have a low frequency. The one that's cycling more quickly will have a high frequency. Let's start with the top wave. So I'm going to look on the left hand side, and every time I see it reach the maximum extent, so when it reaches the top, I'll count 1. So here we go. 1, 2, 3, 4, 5. So we can see that this wave is cycling quite slowly. It takes a long time for each cycle to occur. Now let's look at the bottom wave and do the same thing. So we'll count every time it reaches the maximum extent on the top. We'll count each one of those. So here we go. 1, 2, 3, 4, 5. Much, much, much faster. So we see that the top wave has a low frequency, whereas the bottom wave has a high frequency. So realize that frequency is simply counting the number of cycles that occur each second, the cycles per second, also known as hertz. So just take a moment to watch these two waves and see what a low frequency looks like versus a high frequency. The low frequency looks rather stretched out, the wave pattern, whereas a high frequency, it's more squished together. Now if this were sound, the low frequency sounds would have a lower pitch, like a bass sound, whereas a high frequency would have a higher pitch, like a treble sound. In your notes, I want you to now draw a picture of a low frequency wave right next to a picture of a high frequency wave. If you have not yet finished your drawings, go ahead and pause this video. So a low frequency wave will look something like this. The high frequency wave should look something like this. I've tried to make them have the same amount of energy, so they both have the same amplitude. The only thing that's different is the number of cycles that are occurring. We see that the low frequency wave has only a few cycles, in this case 1 cycle, whereas the high frequency wave has many cycles, in this case 5 cycles. So basically you can count the number of wiggles, and the more wiggles there are, the higher the frequency is. This is of course assuming that the time it took the waves to travel across the box was the same. If they weren't the same, so if one wave was traveling faster than the other, then that wave would actually have a higher frequency. So if you want to just count the number of cycles, you need to make sure that the waves are traveling at the same speed. Otherwise, this little trick won't work. So let's put this all together. I want you in your notes to draw the following 4 waves. A wave with a low energy and a low frequency, do that in the upper left. In the upper right, we have a low energy, high frequency. In the lower left, draw a high energy with a low frequency. And in the lower right, draw a high energy wave with a high frequency. Pause this video if you're still drawing your waves. I'm about to show the answers. So this wave has a low energy. We can see that based on the height. The amplitude is quite small, as well as a low frequency. It's only completed 1 cycle. If we were to increase this to a high frequency wave with a low energy, we'd keep the amplitude the same, but just make there be more cycles. If we wish to increase the energy of this wave, then we'd want to increase the amplitude. So a high energy, low frequency would fill the vertical extent of the box, but it would still only just be 1 cycle. And for making a high energy, high frequency wave, we just take that same low energy, high frequency and just increase the amplitude. So to recap, the energy of a wave is basically how tall it is, whereas the frequency is how wiggly it is, if you want to simplify it in those words. So height tells us the energy, number of wiggles tells us the frequency. The more wiggles, the higher the frequency. The more tall, the higher the energy. And this brings us to our final vocabulary word, wavelength. The symbol for wavelength is the Greek letter lambda, and the unit is meters. And that's because wavelength is a distance. You can see that in the name, wavelength. What distance are we measuring? We're actually measuring the distance of 1 complete cycle of a wave. So for example, the distance from one crest to the next. So clearly we can't measure the length of the entire wave. So instead we simply measure the length of 1 cycle of the wave. So for example, if we start measuring from this crest, we can measure the distance from this crest to the next crest. And that distance is a wavelength. On the other hand, if we decided to start measuring from this 0 point, 1 cycle would not be the next 0 point, it would be the one after that. We'd need to wait until the wave has gone through 1 full cycle. This down and then up and then back again. And that would be the distance of a wavelength. Once again, wavelength is the distance of 1 complete cycle of a wave. And that's it for today's lesson. Hope you guys have a wonderful day. This has been Mr. Keppel. I'll see you in class.